Hi everyone, my name is Cosmas Mwikirize and I'm a lecturer in the Department of Electrical and Computer Engineering at Makerere University in Uganda. And I'm going to present our work on machine learning aided needle tip localization to the ultrasound, undertaken collaboratively with Rutgers University. Now, millions of clinical procedures, for example, nerve blocks and biopsies, involve percutaneous insertion of needles. During these procedures, it is important to keep track of the needle tip location so that it reaches the intended target and doesn't nick anything along the way. This is where image guidance comes in handy, and ultrasound is widely preferred because of its zero ionizing radiation, real-time manipulation capability, and wide availability. However, two-dimensional ultrasound, which is the gold standard, is quite difficult to use because of a limited field of view, where it renders a cross-section of what is otherwise a three-dimensional scene. It also usually requires coordination between the surgeon and the ecotech, since it is difficult for one person to manipulate both the needle insertion and transducer placement. Specific to needles, it so happens that needle visibility is influenced by many factors, including the insertion technique, alignment with the scan plane, depth of insertion, and diameter of the needle. Here we show the challenge imposed by the insertion angle for in-plane needle insertion. Notice that if the target is shallow, aligning the needle with the scan plane is easy, and all the energy reflected by the needle is collected by the transducer. But as we go deeper, it is harder to align the two, and we get non-axial specular reflection, leading to loss of needle visibility. On the other hand, out-of-plane insertion usually gives minimal shaft information and often a low-intensity tip. This makes tip localization even more challenging. And all this could reduce efficacy of the procedure and lead to injury and post-procedure complications. Several approaches have been proposed to solve this challenge. Examples are mechanical needle guides, which have predetermined angles of approach, thus limiting fine adjustments in needle trajectory. Then we have technical relations, the needle and its tip, for example, adding piezoelectric crystals or copolymer sensors to the tip, sending a laser beam through an optical fiber placed inside the needle, or coating needles with highly echogenic material. Of course, specialized needles are usually more expensive. There is also 3D or 4D ultrasound, which, albeit giving a wider field of view, has a lower image quality, lower flame rate, and is more expensive than 2D ultrasound. Then we have optical and electromagnetic tracking systems, which sometimes have large errors, disrupt the normal clinical workflow, and are also very expensive. Instead of using external hardware for identifying and displaying needles and their trajectories, software can detect needles using advanced image processing algorithms. There's a lot of literature out there on image analysis-based methods, but finding the most efficient approach that is robust enough is still an open question. And most of the recent work focuses on the use of machine learning. In our work, we focus on needle tip recognition into the ultrasound, specifically looking at needle insertions where the shaft is not easily visible in both in-plane and out-of-plane insertions. Previously, we have developed machine learning algorithms for this purpose, relying on individual beam mode ultrasound frames as input. And in our present contribution, we demonstrate the use of a learning technique for needle tip localization based on spatial-temporal information. And this is our proposed approach, which consists of two main parts. First, we enhance the needle tip from logical subtraction of the current frame, which acts as the foreground, from the previous frame, which acts as a dynamic reference or background. Now here we achieve an enhanced needle frame without requiring information about the needle trajectory. And then after that, we fuse the enhanced needle tip images and the corresponding beam mode images and feed multiple consecutive fused images to a novel CNN-LSTM framework, which localizes needle tip in the last frame of the sequence. This is the result of the needle tip enhancement step for 4 consecutive frames, yielding 3 enhanced frames. Notice that the tip location shown annotated here becomes more conspicuous. From the enhanced images, we might be tempted to pick the highest intensity in this image as a tip location, but there could also be instances where there are other artifacts as well. And that's why we use a deep learning in the next step so that all heuristics associated with the needle are learned automatically. This is our network architecture. Notice that we input 5 fused images at a time. The network layers are pretty much a standard MO with a series of convolutional layers followed by recurrent layers. We evaluate the proposed method on challenging datasets collected with the introduction of motion artifacts via prop pressure and rotation to mimic the clinical scenario. We use two imaging systems, that is Sonic's GPS with a curvilinear transducer and a Clarius C3 curvilinear transducer. We use 3 tissue types and 3 different needles. The ground truth needle tip location is determined with the electromagnetic tracking system where possible and by an expert radiologist otherwise. Here we show some results. First for 17G needle inserted in bovine tissue in plane. Here is another test sequence. Again, 17G needle inserted in bovine tissue in plane. And lastly, here is an illustration for out-of-plane insertion. Note that accurate tip localization is achieved despite salient motion artifacts that we introduced in this imaging experiment. Our method achieves a tip localization error of 0.52 millimeters and an overall computational time of 0.064 seconds, which is approximately 16 frames per second. We undertook a comparison with our previous method shown in this table and achieved a statistically significant improvement in tip localization accuracy. In a nutshell, although our method shows good performance, we haven't evaluated it on ex vivo data. Thus, in vivo evaluation is still required to fully assess its clinical utility. Furthermore, the needles we used for our data collection experiments exhibit minimal bending, and further evaluation is required on data collected with small bending needles. Lastly, our approach utilizes supervised learning, which requires the labeling of the needle tip location. And a clinical evaluation requires the collection and labeling of large-scale data, which is quite a time-consuming procedure. So as part of our future work, we'll also investigate using a semi-supervised learning method to limit the annotation effort. And with that, I'd like to thank you for listening to me and also appreciate our funders, the Government of Uganda through Makerere University Research and Innovation Fund, as well as Rutgers University. Thank you.